Quantum Foam, Episode 23, Einstein's Relativity.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
This is obviously one of the most important principles in physics. Einstein's General Theory of Relativity. To this day it stands. Einstein's General Theory of Relativity. But it's a theory. It is not a law. Now imagine this. We are going towards the theory of it all. Something that explains all the fundamental forces. Kick it in, kick it out. What do you want to know? That's a theory. But what about the law of everything? Is that the point where you can make a snow globe with your own world, with your own creation, your own design? By your own design, you can create a completely different universe. That's one thing I liked about the Men in Black movie series. They did a good job of explaining how universality, the idea of universalness. You could open up a locker and there could be a whole species in there, living in there. And at the end of everything, we might just be in our own little locker at the edge of some matrix-style, dimensional stretching, switching out of the vantage point of our realm here, where we live on Earth, in this space-time, with our laws of physics here. We don't know even if other realms would be a similar realm that would have 46 constants that we adjust. And, this is the problem. They assume that all these values can just be adjusted all the time, however long. And string theory follows upon the same principle that they do in particle physics and high energy physics. If the math doesn't work out, they change their constants, and everybody does it, but you can't do it. We do that in programming. We are not at the level of being able to program our universe. If anybody is close to that, it is I, or other people who are more concerned with other things at the moment. However, I am trucking forward because it's almost as though I predicted the future. But can't we do that? Like, look around, you see some inputs and outputs and some variables. Can't we do that? You put them into your little equations in your head. Can't we do that? You make some predictions. It's however the gut feeling, the strategizing. Can't we do that? The numbers, people's emotions, however you get the inclination, however you can transform yourself into a position where you can do the dirty. It literally is hilarious. It's ridiculous. But let's get back to what we were talking about here. This was the changing of the epoch, the big one. Out of all these other guys and all this other stuff we've been speaking about, this one was the one. This one was the most recent one. Paradigm shift. This one was the one. And I mean complete paradigm shift. This one was the one. You go from, what are we talking about here? You go from, let's say, the way things are and knows everything and can answer all your questions. The people who are at you go from that level, the people who were at that level that we are aware of, that I am aware of, that you were aware of, that people have been aware of, that people will have had been, were aware of. So we can't do that, man. They did that one. We did it once. You don't have to keep doing that. What? It doesn't even, how do we break the ice off of literally Einstein stuff? People thought that there was a lot of problems with things. They noticed problems with the orbits of the planets. They knew there were several out there, right? But back in Galileo's day, they could see Jupiter, out to about Jupiter. Visual telescopes probably couldn't see much further than that. They could see Venus. They could see the first 5 planets. Jupiter. There were like a couple planets. They didn't know there was shit and stuff out there. What they assumed was out there was nothing. They can't see anything. There's no light reflecting off of it. They don't see any gravitational effects on anything coming from that direction. So they said, this is the way it is, and this is what we know. And that's why it was like, why am I able to see the phases of the moon, but not the moon? We know how the phases of the moon work according to the Sun, Earth, Moon system. How do the phases work according to the Jupiter, Sun, and Moon system? Jupiter has so many damn moons that it was 50-something, 70-something, 30, 80, 90. Like, what constitutes a moon? A piece of shit. What constitutes a planet? What constitutes a moon? Your guess is as good as mine. Oh, this sucks though. But we gotta do it, man. This is why we do what we do. The drive forward. The dissemination of information is fun. What I am doing now is fun. I am regurgitating what I think about a very great scientific discovery that happened in the last couple hundred years, you know?
You have to be willing to go against all odds and against what even the most well-educated physicists say as well. But we all still need to listen to reason as understood by intelligent, knowledgeable representatives of their so-called scientific community.
So what we were getting into before, the smartest people in the world around Einstein's time, this Maxwell guy, James Clerk Maxwell, people were just starting to understand electricity, and they knew what electricity was. There are people who still don't know what it is. It's just power, right? But do you know that it has an AC and a DC and a phase and an up, down, and this, that. So originally there were certain things like direct current is for an electrical connection that is close, and alternate current is for an electrical connection that is far, and it can be transported with minimal amounts of wasted energy due to heat dissipation and other things. So once they figured out they could transport power using a alternate current style of electricity, which is positive, negative, positive, negative, positive, negative all the time, the type of energy is split up. So if you think about it, this is your inflection point. This is your 1 point to 2 point math. This is your 1 point to 2 point thing. One thing to two things thing. Electricity is a thing, but you can have a electric charge of negative or positive. So essentially it's allowing you to do things like in this universe, it's possible to build elements in a table and have nuclear fusion in stars, constantly regurgitate them, blow them up, make stars, make planets. That much we know. But what that does is allows all these other elements to be created inside the sun, up to iron, and back and forth. And then the other ones are done through other processes in the suns and during different cycles. It goes up and down and up and down. The bigger stars have bigger systems, the smaller stars have smaller systems. Proton-proton chain just gets into that kind of thing. The actual system of the nuclear fusion, which is a system that is quite damn efficient, yet it's the most violent thing in the world and we can't be around it. And the only way to contain it is to have enough of it in one place to where its own gravity contains itself. Unless we can manipulate gravity on that level, you can't do it like they did in some of those Spider-Man movies, where you have like a sun on the surface of the earth. Think about that. If there was a sun that big and that dense, what is that dense? Density is a number, so you got to give it a number. You can't tell by just looking at it. Oh, that's dense. How do you know? Give it a density. People like to go from 1D to 2D, or people like to go from 2D to 1D, and 3D to 2D, and things like that really quick. You can't just dismiss that other dimension so easily, yet we can do it. We do it all the time. We get back into this relativity. It's a metric tensor. They are equations that were worked out for distances. It started meaning something different when we're talking about a distance within a space-time. When you talk about it like that, there are different aspects. doing different things with these equations. We've known about the Pythagorean theorem for a long time, how a triangle can add up a squared plus b squared equals c squared, but it fails us during certain substitutions of these equations. What is the orthogonal base vectors that we are working with? What are the base vectors? R. What is the base vector? The base vector is R with an arrow over it, and we regard it as the squared magnitude of R. That's the entity of the vector. That's the substance of what it is. This gives it corporeal form. This is a corpuscle, as you guys like to say. It's a corpuscle. It's a corpuscle. What is a corpuscle, man? It's a corpuscle. That makes me think of it's a corpuscle. Like a big pile of goopy gray matter that you can touch. It's a corpuscle. That's a corpuscle. I don't get it, dude. It's a corpuscle. I don't think that's what they mean by that, man, but that's what I think of when I hear that. What implications did this have? When was this? Most people know this story. 1905, 1915. Einstein was 26 in 1905, and he was working as a patent clerk, and he released, 5 papers or something?
3 papers, actually, at that time.
Published them, explaining basically that light is part of the background of space-time. What? Everything that we see, what? Energy with no mass, like light, what? Radiation, visible light, gamma rays, that kind of thing. All of that doesn't have any mass. It's a wave in space-time. It is part of space-time, which means that it is not ether. The double slit experiment shows interference patterns. We've went over the example of your speed in space. We're all in space, right? We can see around us. Obviously, there's something here. We move close, it hits us.
Michelson and Morley experiments, right angle with the Earth's direction of spin, etc.
Now we're in that distance, spatiotemporally speaking. Everybody understands this concept. If you got limbs, if you got extremities, spatiotemporally speaking, whatever, a couple feet off of your body, spatiotemporally speaking, is your personal space. Spatiotemporally speaking, around bubble encompassing your body. That is the size of us as entities. Spatiotemporally speaking. However, we have gone into the age of the quantum where we can store massive amounts of information on things that are the size of wafers of gum, chewing gum. In history, we couldn't get enough sources. There was few and far between, and all of a sudden we passed the apex of onslaught of digital dissemination of information where there's too much to read. There's too much to even know what you're even knowing. So you gotta go through it all and be like, okay, this is what we know. After reading all this other bullshit, you don't need to know this stuff. Trust me, why would I be doing this at all? I'm doing this because I want to fucking know, man. I don't want to lie. I don't want history to go down as wrong. I want people to know what happened. And so, strategically or not, credibility or not, we get back into Einstein's theory and how it triumphs. After these predictions, this was the way science is supposed to be done. You make a prediction, you come up with a theory, you say all these profound things. People are like, so you've done in a world-changing paper, everybody does that, right? He did, and then people started to catch on. Hey, this has some stuff to it. This might actually be the way it is. The only way to find out is to observe experimental evidence. And so it could have been done sooner, but remember, at this time in the world, World War I was ramping up and various things were happening around this time. So without getting into too much of that, there were scientific crews out trying to take observations, and various parties were having issues, and they were going to try to observe experimental evidence of relativity in gravitational lensing of stars that can be seen on the backside of the sun and gravitationally lensed around the sides of it. Stars that are known to have been there, stars that we have taken previous photoplate pictures of. And back then they had photoplates, which essentially was a material that could change contrast based on photons being put into the emitters. And so this was going to allow the proof of relativity. You can look at a piece of mass, like a human, as a wave, and you can get into the quantum mechanics of that, but as far as relativity even, you are a wave of mass through our space-time where we're at. Space-time where we're at.
That is fairly accurate. Thanks for explaining a nice backstory for me, Doctor.
One of the biographies that he recommended to me was the one on you, Mr. Einstein, written by Walter Isaacson, but it's break time.
Obviously, this is the midpoint of
Episode 23, Einstein's Relativity of Quantum Foam.
quantum foam.
And this is independent of the background. The background is part of the system that is what we see in light and feel what we feel with matter, with the moments of inertia that matter can create and does create, and the interactions of gravity as a whole. The theory of gravity is the next theory. Gravity as a whole, the theory of everything, is a theory of gravity, macrogravity mixing with quantum gravity.
It will be built upon the fundamental gravitational metric tensor matrices included in the new quantum computers within the operating systems, then available as a quantum calculator.
Relativistic macrogravity and Newtonian and Kepler physics mixing with quantum mechanics, Dirac, Schrödinger, any of the string theory guys, kind of math, background dependent. What is this great attraction that we are moving towards? Why are we moving around like a spiral through space-time? Are we just another particle in a larger system that mirrors ours? Once you magnify out a certain level relative to where we're at now, do you see yourself again? Is that how, in fact, you go forward and backward in time? When you go a certain distance, when a light year is significant because it takes light a year to travel that much through space, so there's that much space. So beyond that point, we can understand a year because we can count years. Human life, 80 years, pushing 50 to 100 years is average. Somewhere right in the middle of there, 75 is average. So we can count years. Oh, the sun went around once. Okay. We can count the number of winters if we think about it for a minute. So our time period that we're seeing through space-time is only that long, according to the units we've given it. So some other things here. They've named a few things. Einstein's cross, the quasar in Pegasi constellation. It's a pretty good example of this gravitational lensing. It's 8 billion light years from Earth. It sits behind a galaxy that's 400 million light years away. It's behind. So basically 4 images of this quasar appear around the galaxy because of the intense bends coming from the quasar. So we get to see a supernova blowing up 4 different times. It's pretty cool. Something like that is to prove that it bends light according to the way Einstein predicted with these equations.
I worked very hard on those.
And so other things that are important, gravitational waves, 2 black holes colliding or something. You view this with a laser interferometer gravitational wave observatory, LIGO. This is in 2016 they found those. Remember, these are not gravitons, because that is a particle. That particle, more than likely, is only constructed with mathematics, with nothing more. However, at the moment, we don't know how to describe a particle that spins around twice. Everything it's made of spins around twice in and of itself. And these are disappearing fields and stuff. So, how do you calculate something that you can't view? The problem is you have to give it a mathematical identity. That mathematical identity might be the mathematical matrix structure that is the graviton particle. That is what I mean by that. But back to this. LIGO spotted the first confirmed gravitational wave September 14th, 2015. This is based out of Louisiana and Washington, a pair of them. They were upgraded recently for that. This is fairly recent shit, man. They basically provide evidence for pairs of black holes spiraling inward and colliding. This is fairly recent shit, man. And we can see them and feel them at the same time. That's how they know that they can see them. I mentioned this before. This is fairly recent shit, man. But you can put 2 and 2 together. This is fairly recent shit, man. You look in a direction and something goes ding. And you look in a direction, ding. And you see it at the same time. Ding. That is ding. Proof that 2 and 2 is 1 and 1. Ding. According to this relativity, a fast-moving object appears shorter along the direction of motion relative to a slower-moving one. This effect is essentially very subtle and unnoticeable until these objects travel closer to the speed of light. What I don't get is when it comes down to the nitty-gritty and that point between understanding and total confusion, there may be too much information for us to be able to discern any recognizable pattern. And so far, we don't see any pattern in the microwave background radiation.
We think asymmetry, but we see nothing but symmetries in space.
We see a bunch of random shit and we try to calculate a pattern and there's none there. Quantum jitters, as Brian Greene calls it. The stuff that comes out of the quantum and makes electrons appear in certain locations that are unpredictable and that are different each time. They figured this out with the chemistry. How can you create an element from another? That's alchemy. How can you create gold? Make everything turn to gold. What? Gold. Gold is pretty damn conductive. Gold. Silver supposedly is more conductive. Gold. That's besides the point. Gold. So E equals mc squared. A quantity of energy is equal to a quantity of mass times the speed of light squared. The speed of light squared thing is to take care of the magnitude of what light is by the mass. So that mixed with the mass is the energy. So mass and energy, different types of particles mixing together in different amounts, is equal to your energy. Nuclear weapons. Nuclear fission. Fermi, 42. Enrico Fermi. I am particle physicist. We make nuclear weapons to destroy world. I am particle physicist. You want to win or lose? I am particle physicist. There is no you win, they lose. I am particle physicist. They win, you lose. I am particle physicist. There is only you or lose. If you want that button, I got that button right here. I am particle physicist. But I need equanimity. I don't know. They did it, we did it, they did it, we did it, and they did it. Then we do it, and they do it, and then nobody does it now. So hopefully that is the way it stays. They did it, we did it, they did it, we did it, and they did it. Then we do it, and they do it, and then nobody does it now. And so mastering this fusion, get into more of that at another point. So what does this relativity make us think of? Essentially like a trampoline and a ball rolling around it in the pivot of the indentation that the heavier ball made. Heavier ball makes a bigger indentation on the quote-unquote 2D lattice that's supposedly representing the 3D lattice of space-time. And then we're viewing said art on a 2D screen or potentially within a 3D environment on a... So we're within a 3D environment on a 2D screen representing a 3D picture which utilizes a 2D grid that demonstrates gravity. So essentially it's a trampoline and a ball. It's like Mercury and the sun. This explained the offshoot behavior of Mercury and how it didn't fit with Newtonian physics. That was like, what? Something's going on down there. That's that one issue. This thing is good, but that, what is that? What that is that the sun's gravity affecting Mercury. That it is the location of planet X where the aliens are secretly controlling our entire solar system. It is a Hubble photo of a galaxy distorting galaxies and quasars behind it. It's proof, mother truckers. How is it that you see the same thing 4 times? It's a mirror image because of something that's obviously in the way, a gravity well. Light bends itself in space, okay? We don't know where black holes lead, but we do know that light bends now. You can bend light with massive amounts of gravity. So how do we master this gravity? Einstein's theory of relativity, special theory of relativity, is how it pertains to light. And so general relativity included acceleration and how massive objects warp space-time. He finished up the theory when he made it the general theory of relativity. And so 1905 really was just the laws of physics are the same for all non-accelerating observers, which essentially means that you can be in an elevator falling and still think that you're walking around on your own gravity. Because if the acceleration speed of the falling elevator is taken into account and then you just have gravity left, that's the same as sitting on the Earth when you just have gravity left. So it's indistinguishable. He added acceleration and how big suns and stars and black holes and quasars and stuff can warp space and cause gravitational lensing and other such things. This very, very peculiar effect that is caused by general relativity, and why this man was heralded worldwide as a genius, and now it is a name that's synonymous with being a genius. Einstein.
According to your metrics, I would have about an IQ of 170.
Well, I think I finally cracked your issue, old man. Shall we not? We shall. I've got the papers before me, but I am in the middle of concatenating them. So, as a result of E equals mc squared, a fast-moving object's mass appears to go up relative to a slow-moving one. It's like its moment changes. This is due to the fact that increasing an object's velocity increases its kinetic energy. It's got more energy in it. If it's moving faster, it's got more energy in it, kinetic energy. And if energy is mass, it's got more mass. So it's got an effect of a different mass for a different speed. But everything's the same. No, it's not. It's all relative. That is what we found out. This increase in mass is why matter can't move faster than light. This is where this infinity happens. The mass increases with velocity until the mass becomes infinite when it reaches light speed. An infinite mass would require infinite energy to move. It's just not how it works. You would think it'd be impossible, but obviously you can move things in and out of space-time, but how do you move mass faster than the speed of light in a space-time? You might not be able to do that. That's kind of what Einstein's saying here. The moral of the story is that space and time are part of one continuum called space-time. This allows very peculiar things which we are going to experiment a lot with here in the virtual world, but this is an effect that they call the frame dragging of space-time. What? Space-time can be thought of as a grid or fabric, and then taking a picture of that. The frame.
Frame dragging?
So theoretically, if you're splitting up time in frames, then the gravitational lensing of these frames can throw images in random places, specific places within the view of the telescope. It makes shit look like, what is going on here? It's gravity throwing mass around and light around. It's gravity throwing light around. Pretty crazy shit, man. And this is all because of relativity and the effects of space-time, and how when you travel 0.5 c or 0.8 c, the vantage point from us here, and then a random object way far away in space is traveling relative to us 0.8 c. We look out and this object's going 0.8 c faster than us relative to everything else on average. If that's the case, then that other object appears more like a wave, and it's skinny like a light wave. The mass and everything, the galaxies, the mass, the substance, all of that appears skinny and closer to a light wave, because if it were to go the speed of light, it would be a wave, and it would never actually approach the speed of light. And I know this because I just dumped out my pop, and relative to you guys, that does not matter. So these are very weird things that have been explained due to this. Pretty profound, pretty epic, and pretty sweet if you think about it. Thinking about different timepieces, the moving timepiece runs more slowly than the stationary one. This is the only possible way that we know of to technically travel into the future. Relative to the Earth, a rocket ship could travel out at 0.8 c or 0.9 c and then come back after a certain number of years, and the person on board will be younger than the people here back on Earth. We will have aged and died, and they will be into the age of the future.
The twin paradox.
So if you want to go into the future, just travel outside of the Earth at point whatever c for so long, then head straight back, and then once you get back, the Earth will be in the future. We don't know how to do this yet. There still is tidal forces and structural integrity degradation that happens when you apply forces to materials. A spaceship that moves at 0.5 c and it suddenly jerks to the left is ripping everything all to fucking hell. It doesn't matter if it's the strongest material in the world. We need to learn how to manipulate matter, gravity,
density, mass, and energy on this level.
The idea is for the new teachers to instruct the youth of the future to learn accurate English, physics, and mathematics,
using power of a level 1 or 2 society. We wouldn't need a level 3. We need to be able to utilize energy on a planet-wide scale, which means ditching fossil fuels and other such things for reasons for fuel. Planet-wide scale and things. Planet-wide scale. That is besides the point. This pretty much ends this. And this is it for episode 23,
Einstein's Relativity,
of Quantum Foam.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.